So as I said, Fourier transforms and Laplace transforms are special cases of integral transforms. So first, let us discuss integral transforms. Integral transforms. Integral transforms. So what are integral transforms? Integral transforms are let capital K, which depends upon P and T, be a function of two variables. Be a function of two variables P and T. Be a function of two variables where P is a parameter and this parameter may be real or complex, and P is independent of T, independent of T. The function f of P defined by the integral. Defined by the integral. And what is the integral? The integral is this. F of P is equal to integral from minus infinity to plus infinity K Pt multiplied by f of T and integrated with respect to the variable T from minus infinity to plus infinity. This is called the integral transform, and this is denoted by T open braces f of T. So this integration is called the integral transform of the function f of T, and is denoted by capital T in braces f. So this is what we mean by integral transform. One of your microphones is on, so let me mute you. Okay. So this is what we mean by integral transform. Here, this function K is called the kernel of the transformation. So let me write it down here. The function K is called the kernel of the transformation. Is called the kernel of the transformation. What does it do? The function f of T in the T domain. Well, T domain means f is a function of T. So the function f of T in the T domain is transformed to the function f of P in the P domain. P domain have it here. Small f is a function of P and capital F is a function of T. So capital F, which was originally a function of T, has been transformed to a new function small f, which depends upon small p. So we say capital F is in the T domain, small f is in the P domain. By choosing different kernels in different ranges of integration, we can define several transforms. So let me write it down here. By choosing different kernels in different ranges of integration. Several transforms are defined. Let us discuss some example. Laplace transform. First, let us discuss Laplace transform. Laplace transform have the here f of s is equal to integration from 0 to infinity e to the power minus st f of t dt. Here s can be a complex number. This is a Laplace transform. And what is the kernel here? The kernel here is e to the power minus st when t is greater than 0, and when for values of t less than 0, the kernel is 0. So the kernel is defined for values of t from minus infinity to plus infinity. For Laplace transform, for values of t from minus infinity to 0, the kernel is 0. And for values of t from 0 to infinity, the kernel is e to the power minus st. So this is Laplace transform. Next, we have Fourier transform. Fourier transform, here let me write it as omega. This, we have a normalization constant 1 by 2 pi, integration from minus infinity to plus infinity, e to the power minus I omega t f of t dt. This is Fourier transform. So if we choose the kernel as e to the power minus I omega t for all values of t from minus infinity to plus infinity, we get the Fourier transform. There we go. Next, we have Mellin, another transform, which we call Mellin transform. M-E-L-L-I-N, Mellin transform. F of s equal to integration from 0 to infinity e to the power s minus 1 ft dt. This is Mellin transform, where the kernel is t to the power s minus 1 when t is greater than 0. And for values of t less than 0, the kernel is 0. So this is Mellin transform. Then let me take a new sheet.